Let me take you back to a time when we thought that the force of gravity could be simply stated as mg, where g is 9.8. Then we learned a little bit later that, well, the force of gravity really isn't just mg. Newton came up with this universal law of gravity, the g, m1, m2 over r squared, that guy. So that applies to the entire universe. The mg is the simplification on the surface of the Earth. And so we're going to apply that to our energy principles. And to do that, we're going to look at me hanging out on the Earth's surface, having a good time. I'm defining the ground to be 0, so I have no potential energy when I'm on the surface. But then I get bored and I decide to go out to space, and now I'm out here. A distance r from the center of the Earth is my gravitational potential energy, mgr, where r is this distance away. Well, not really. No, we can't say that would be that term because, well, g is no longer 9.8 meters per second squared when I'm out here. And plus, if we define this surface to be 0, then by our old equation, mgh would be our potential energy. So this kind of breaks down. We need to go back to the force of gravity equation that Newton came up with that works everywhere, g m1 m2 over r squared, and take a closer look at the gravitational field strength. So we picked out a part of this and said that's g, that's a constant based on whatever planet is pulling another object inward. The gravitational field strength here is this g constant 6.67 times 10 to the negative 11th. The mass of the planet that's pulling and the distance that an object is away from the planet. So if I take that gravitational field strength and I say, well, I'm way out here, what is my g? Well, I could take the mass of the Earth and I could take this r and I could figure it out. Now that would go in the place of my mgh. So this would be some g that should be less than 9.8, and I could use the r, the distance I am from not the surface, but from the core of the Earth. That would give me my potential gravitational energy, and this applies to anywhere in the universe, or two objects will feel some gravitational tug between them, and that's stored in potential energy, and it's divided by the radius squared, or radius, I'm sorry. Notice here that this radius will cancel out with an r squared on the bottom. I'm just left with one r on the bottom. So by convention, we talk about potential energy as a negative g m1 m2 over r. See if you can make sense of this. I could call this either positive or negative, so these are the two graphs that I'm trying to consider. I will define the 0 to be when I'm infinitely far away from, in this case, the Earth. When I'm infinitely far away from the Earth, I have 0 potential energy. And when I get closer to the Earth, I get some potential energy stored up. Now, if I considered this equation to be positive, this would mean when I'm some distance away from the Earth, and I lift up an object, let's say that this is when I'm at the surface, I lift something up, I should be giving it potential energy, but that's not what we see here. If I lift something up so that r is increased, the potential energy goes down. That doesn't make sense. So that can't be the correct sign for potential energy. So let's consider the negative version. If I'm at the surface of the Earth and I have that much potential energy, I lift something up, oh, well, now it's increased in potential energy. So the negative sign is conventional, and it makes sense with what we've already used in mgh. When I lift something up, I'm giving it some potential energy. And you'll see why in my next video, why that negative sign helps us out in some analysis of an escape velocity to get off of the surface of the Earth and completely away from the Earth's pull. All right, guys. Until next time.